Hey guys, welcome back. Today we're going to talk through the temporary sediment basin and how to design this for your plans. There's a little bit more work or design that goes into specifying this on plans than some of the other BMPs, so we wanted to walk through an example so that you can see how to do it. So let's follow along with Casey as he shows us what to do. Let's learn.
Welcome back, everyone. Today we're going to be going over the sediment or temporary sediment basin design and temporary sediment trap design. So for this project, we're primarily going to focus on temporary sediment basin design, but we should be able to talk about both here. So we have an erosion control plan that was started, and I'm sitting here working with Parks, so we're probably going to have some dialogue back and forth, basically recording this video and also using it as a teaching opportunity. We just got rid of what he had before. We had a SD3 or temporary sediment basin right around here, and then another temporary sediment basin right in this low point. But if we go to our phase 2 here, this is kind of where that, I probably shouldn't have deleted it before I started the video, but this is where that temporary sediment basin was before. So what we're going to do is we're going to use a very common strategy that we use like all the time whenever we're doing our erosion and sediment control plans, which is using the ponds that are eventually going to get graded in phase 2 as our sediment traps in phase 1. So effectively what that accomplishes is the contractor can go out during phase 1, they can grade out a portion or even the entirety of their ponds in phase 1, right? So they're that big hole that they dig out, because that's all it is, they're just digging out a big hole, doubles as the sediment trap or basin. And then whenever they move on to phase 2 and they have to grade in their ponds, they either just dig out that hole a little bit bigger if needed, or just leave it as is, and now that's the detention pond instead of the temporary sediment trap. So this kind of saves the contractor time and money, and thus saves our client time and money, because the contractor doesn't have to dig out a big ass hole over here and then turn around and dig out another big one later on and fill in the old one, whatever. So that's kind of the thought process behind using our locations for our ponds as our temporary sediment traps and basins. Here we have a little bit of a unique case though, because we have a detention pond that has a retaining wall as, you know, three sides. You can see this red retaining wall that runs around like 80% of the perimeter of our pond, except for this access easement here. So what we're gonna do in the phase 1, so if I move back over to phase 1, is we're just gonna have to grade in a hole that's like in the same spot that they're going to have to grade out, right? So we can see from these elevations that it looks like this is the 46. So the bottom of this pond here is going to be at 46. So if I go back to our phase 1 here, we're just going to look for the 46, which we can't do because of the XREFs. But 1045 is right here, so this is the 1046, is this contour that runs right here. So from our 1046, we know that's going to be the bottom of our pond. So if we keep the bottom of our sediment trap above that, then they're not going to have to fill anything in. So I'm going to go back to our phase 2 here, and then the top of this detention pond is like roughly, there's the 60, so 62, 64. So from 46 to 64 is the bottom and top of our detention pond. So for our sediment basin, we can keep it within that range, so they won't have to do any extra work when grading out the detention ponds. Now if we move up north here, you can't see it for whatever reason, but there's going to be a very small pond like kind of right here in this area. So what we're probably going to do is, again, grade out a temporary sediment trap or basin right here that's going to be in the same location as our pond. So we're going to start with the SD3 and then move to what's probably going to be an SD4 here. So I'm going to take this opportunity to go over the differences between the two. So if you navigate to support, company docs, policy, and then civil guidelines, or excuse me, construction documents, then there should be a 7.3 workflow erosion control plans, where it outlines what circumstances you're going to use an SD3 versus an SD4. So an SD3 refers to a temporary sediment basin, and then an SD4 is a temporary sediment trap. So if we're working with a site that's an acre or less, typically we submit it submit it without a temporary sediment trap or basin at all, because we believe that silt fence is enough to accommodate all the required sedimentation storage. Sometimes jurisdictions don't like that and they want to see a temporary sediment trap anyway, but usually if it's an acre or less, that's what we're going to start off with, is just by achieving the sediment storage just with silt fence. If the area draining to that hole in the ground basically is between 1 acre and 5 acres, then it's an SD4, also known as a temporary sediment trap. And then if the area draining to that temporary sediment blank is 5 acres or more, then it's going to be a temporary sediment basin, also known as an SD3. So the SD3s are way more involved, so it's pretty common that we will like put it'd be better for us, like say for example, if we had a site that's 9.5 acres, so just under 10 acres, and we can perfectly split the sedimentation to go to 2 basins that are at 4.25 acres draining to them each, so they both don't eclipse that 5 acre drainage area, so they're both SD4s. We're going to do that every time over having one SD3 that takes on all 9.5 acres. The reason for that is the SD3 requires, and some jurisdictions won't require you to fill it out, but if you submit to GSWIC, then they're going to require you to fill out, in a lot of cases in the state of Georgia, you will submit to GSWIC. They're going to require that you fill out an SD3 design sheet, which is like a big long PDF that you have to input a bunch of information. We have an Excel sheet for it too, but either way, it's a pretty tedious and long task. Whereas the SD4 is a much, much shorter design process. It's so much easier to do. It leaves less room for them to have comments. And so forth. So I'm also going to open up the erosion control. So I'm just going to go to support, codes requirements, should be erosion, and then Georgia GSWIC, and I'm going to open up the erosion field manual 2016, which is the most recent field manual, and then I'm just going to go ahead and search for SD4. So there is only one version of the SD3, which is what we were just talking about, the temporary sediment basin. But temporary sediment traps have multiple different variants. So there's SD4 A, B, and C. So the SD4A is, and they're all the same thing. They're just a hole in the ground, but they have different outlets and different ways of filtering out substances from runoff and sedimentation. So it kind of depends on like the geography and the ground, basically like the grades and topography of that area, which one might be the best to do. Well, we've done all of them. I personally would say that we probably do SD4As the most, but they just have different outlet types effectively. So if we go to the field manual, not the manual, it should have some more pictures for us to reference. So I'll go to SD4, and then we'll go to SD4A. So this has an overflow outlet, and they have different limitations. SD4B is the combination outlet, and then SD4C is a rock outlet. So typically we do SD4Cs more than anything else. And then the other key thing to note is that the drainage areas are limited. So if you have more than 1 acre draining to it, you have to do an SD4C. So if you fall into this range here between 1 and 5 acres, you have to do an SD4C. And then if you have less than 1 acre, but they do want you to provide a temporary sediment trap, you can do an A or a B. So as you can see here, maximum drainage area for SD4B, 1 acre, maximum drainage area, or limited to small drainage areas less than 1 acre with gentle slopes for SD4A. So those are kind of the determining factors on which temporary sediment trap you're going to use between the 4. And then they provide some details here for you to reference. And then I personally have done a few projects that have used basically all 3 of these different types. They're all pretty simple to design. I believe they call out in these details which is which. So this one's the overflow outlet, combination outlet. So this one's an A, this one's a B, and then the rock outlet here is a C. So for this project, we're just going to go ahead and navigate back over to our project. If we take a look at the grades, so I'm just going to go back to phase 1, make it a little bit easier to see. If we take a look at the grades here, we have a high point here where this existing house is. If I'm not mistaken, this house is on the property that we're working on because we're putting a pond here, like in their front yard, effectively. But the house is not to get demoed; it's gonna stay. So we have a high point here where this house is, and everything in the front yard of the house is draining this way, right? And then everything on the south side of the house, as you can see, it's like one big long slope that's sloping down as we move from front to back of the site, and then it's also sloping from right to left, or kind of from top right, it's sloping down to the bottom left. So because this is our high point here, and then it's just a pretty gradual slope from like top right to left, or to bottom left, and then from the entrance of the site to the back of the site, we're basically going to have this entire area. If we split like from the property line, we're going to have effectively like this whole area to the property line here. Okay. Just draw this line. Everything below this line is going to be draining down this way, and everything north of this line is draining up this way. So if we go ahead and isolate this guy, and then I can't turn on the property line because we have this XREF thing, so let me just draw. I'm just going to trace the property line right quick. Super quick. We're just going to roughly trace it. We go all the way up like this. My cat's freezing. This is great. Alright. All the way down to here. And I'm going to isolate this guy. And then we're going to connect it so we can find the area. So I'm going to grab this. So this entire northern basin, if you will, that's draining up to the temporary sediment trap we're going to have here is 0.67 acres, so it's less than an acre. So we can effectively claim that we're getting all of the sediment storage from silt fence, which is probably what we're going to try and do. But if later on the jurisdiction comes back with comments and says, no, we don't like that, we want you to provide a sediment trap for this area, then it's going to probably be that SD4A sediment trap that's for small drainage areas with gentle slopes. This one doesn't really have gentle slopes, so you might end up doing the SD4B. But we will touch more on that later. So I'm just going to break that there and there, so I still have my separation line. And then we're going to go back to phase 1. So that was what, 0.66 acres, and the entire acreage of the site is, what's the entire acreage?
7.02.
7.02. So 7.02 minus 0.66 is 6.36 acres, which is above 5 acres, which means we're going to have an SD3. It's going to have to be an SD3 that's down here that's picking up everything south of this split line that's draining down this way. So lucky for us, this site is somewhat simple to design, basically, as far as the erosion and sediment control goes. So what we're going to do is we're going to have a diversion ditch that's going to be on this western side of the property here. So the diversion ditch is going to basically pick up all of the sediment that's running from right to left, because if you look at the slopes, our water is flowing perpendicular to the slopes. Like right here, it's going to run from right to left and then into the red line here, which is our diversion ditch that I'm currently drawing in. So I'm just going to draw in this diversion ditch, which is just going to pick up all this. I'm going to keep it out of this stream buffer. We don't have to keep, we got to keep it out of this stream buffer here, I believe, but we can just navigate it like here to here to here, and then our sediment trap is going to be somewhere right in here. So this is going to be our diversion ditch. I'm going to go ahead and make that directional arrow. I'm actually just going to go ahead and put it on that layer, and then a directional arrow. Cool. So there's our diversion ditch. I'm going to go ahead and offset that guy 1 foot and 1 foot, just so it's a little easier to see. Make that continuous cyan. So there's our diversion ditch that's going to carry water into our temporary sediment basin that's going to be right here. And then the process for using the pond, like I was saying before, because this is a unique case where we have the retaining wall here, it makes it a little bit more tricky because we're just going to have to grade in like a hole in this spot. But if you have a traditional detention pond that just has 2-to-1 slopes and like a pond berm, you can just copy those contours and then just paste them into your phase 1, and then just maybe delete some of the bottom contours so it's not as deep, because it likely doesn't have to be as deep as the pond is. And then you can just leave those contours there, and they're copied like exactly like the detention pond is. So then the contractor is literally just getting a head start on grading their pond. It also just looks cleaner as you transition from phase 1 to phase 2 to phase 3. So for what we're going to do is I'm going to go to phase 2, and as you can see, this diversion ditch is kind of taking us into like right where the sediment trap's going to be. So I'm just going to trace out like what area we're going to have to keep the sediment trap in, like our outer bounds, if you will, for where our trap needs to be. So it's just going to be something like this, like the way that the pond runs, all the way to there. Okay, and then I'm going to go back to phase 1. So our SD3 needs to be within this area. So for the SD3, I'm going to go ahead and go back to the codes requirements, erosion, GSWIC, and then we're going to go to SD3 calcs. And then we have the XLS file here, this Excel file that we use a lot of the time to do this, but you're going to have to provide to GSWIC, typically if they ask for it. It's going to have to be this sheet here, the temporary sediment basin design. Oh no, that's the manual on it. Here we go, design sheet. This big PDF here where you have to input all of this information, which really sucks. So this is basically why we're always going to try and split a site up in order to make it 2 SD4s versus 1 SD3. So this site being 7 acres, that might be possible. So we're just going to kind of look at the site here and see if that's doable. One thing that is pretty typical is we can't locate our sediment traps somewhere where they're going to have to grade out a road or pad grade out homes. So here it's kind of a cram site, so it's pretty hard. The only real convenient location to have a temporary sediment trap or basin is right here where our detention pond's going to be. What we could do is try to have like some sort of really small temporary sediment trap that's like back here behind these houses. It's like really small and narrow. There's nothing inherently wrong with that, but the issue that you get into is this is only going to pick up runoff from this left side of the road, basically. We're at 29 here, so yeah, everything's kind of flowing down more, and it's going to bypass this guy and then flow down. So it's just because of the shape of the site, it's just kind of awkward to try and split it into 2 SD4s over 2 SD3s. There might be a way to do that that makes sense, but for time's sake, we're not going to spend too much time thinking about it. So we're just going to go back to our phase 1, and our strategy moving forward is going to be silt fence up here to capture the majority of this runoff. So we're going to have silt fence basically all the way up to where the construction exit is going to meet the road. So we're going to have silt fence. It's picking up all of this runoff up to the property line, probably some like up to there. And then we're also going to have silt fence on this side of the construction exit. It's just picking up all of that. Okay, so all of this is going to be silt fence. Okay. And then as far as the sediment storage that provides, if you come down here to our liters, we're going to have a silt fence storage multi-liter here that's like already, this guy's the one that we want, that's already built for us. So I'm just going to grab that guy and I'm going to place it right here. Go ahead and put a background mask on that to make it look a little nicer. Okay, and then I'm going to click on this guy. So the length of that is 140.8 feet. And then the length of this guy is 152.86 feet. So we have 293.66 feet. So we're going to round up to 294. Don't tell anybody. No, I'm just kidding. We're going to round up to 294. So we've got 294 linear feet of silt fence provided. The fence height is going to be 2.5 feet. The storage per linear foot is going to be 1.5 times 6 over 2, which is 4.5 cubic feet per linear foot of silt fence. And then the area draining to this was 0.66 acres. So the minimum storage that we have to provide is going to be 0.66 times 67 cubic yards divided by 0.167. So that's going to be 264.7 linear feet. 264.7 linear feet. And then the sediment storage we provided is going to be greater than that number because we provided greater than 264.7, so we're good. Sediment storage that we provided is going to be the length of our linear foot. It's 294 times 0.167, which is going to be 49.1 cubic yards. Change that guy to 294 linear feet. Cool. So we are required to provide 265 roughly linear feet of silt fence, and we provided 294 for this area that's draining into the silt fence. So we've met the required sedimentation storage or sediment storage for this little area. So that's fine. That's good to go. So we're going to go ahead and throw the block on there for the non-sensitive single row silt fence and label it. I'm going to set this guy to be parallel to that, which did not work at all. So we're just going to roughly rotate this until it's kind of like close enough. As such, I'm actually going to throw that like right there. Then we're going to move this multi-leader, throw a background mask on that as well. Cool. And then I'm going to copy this guy over to here. Like that. Cool. Okay, so now we've got the sediment storage for this like top basin area provided. So everything else is going to drain down directly into our SD3, or it's going to drain over here into our diversion ditch, which is then going to carry it into our SD3. So for our diversion ditch, we're going to also go ahead and label that guy. So it has to be 1% slope minimum. DI is the symbol for it. So I'm just going to go ahead and throw that guy right there. I like to rotate for silt fence and diversion ditches. I like to rotate the block. I think it looks a little bit cleaner like that. And that's going to get called out. I'm going to leave this label as red because we have this C detail on sheet C6 point. I don't know what detail the diversion ditch detail is going to get put on for this set of plans yet. So actually what I'm going to do is I'm going to leave it by layer, but then I'm going to make this part red so hopefully someone sees it and remembers to change it. And then I'm going to continue to paste this guy. So real quick, just to make it easier to paste, copy it like this. Paste that guy like that. This is a super long diversion ditch, so we're going to provide that block that calls it out multiple times. We're also going to provide that multi-leader that calls it out multiple times. So we're just going to label that a few times. Kind of the fun of erosion control plans is just like putting blocks everywhere and labels and then like making it like a puzzle. I've also found that a lot of the reviewers that review our erosion control plans, like they kind of just like to see that you put a bunch of symbols on there and you're like providing a lot of BMPs and not really, you know, what your actual strategy for providing erosion control is. So do with that information what you will. Make it look pretty, basically, is what I'm trying to say. And usually they'll be nicer and not provide as many comments. So I'm going to call that out multiple times. And now we can go ahead and we can start to design our SD3. So we're going to go back here to this temporary sediment basin design sheet, and I'm just going to go ahead and start working on it. So I'm going to move this guy like over to the right there. What's the project number for this again?
24322.
322. Okay. Basin number, we'll just say south because it's kind of like south and north basins. The total area draining to the basin was 6.36 acres. The disturbed area draining to the basin, well, we don't know the answer to that yet, but we probably should. But that's going to be the disturbed area that's draining to it in phase 2. So we're going to have to look at our phase 2. So the volume, we're going to have to compute the minimum required storage volume, which is going to be 67 times the acres draining to it. So 67 multiplied by 6.36 acres, which is going to be 426 cubic yards. So we're going to have 6.36 acres, 426 cubic yards, and then the volume of the basin at the clean out. So in every temporary sediment basin and trap, there's going to be a clean out elevation. That's like once the bottom of the sediment basin or trap fills up with sedimentation to a certain elevation, the contractor is going to have to come and scoop out all that sedimentation and get rid of it. So the clean out elevation is a third of the volume, so it is 22 cubic yards times the number of acres draining to the basin. So it's going to be 22 times 6.36 times 6.36 acres, which is 139.9 cubic yards. This guy was 426.1, we'll be precise. The minimum riser crest elevation is going to be determined by the stage storage relationship, so that's what we use the Excel sheet for, so we're going to leave that alone for now. The clean out elevation is also going to be determined by the stage storage relationship. We'll go over how to do that in just a minute. And then the length of the riser is going to have to follow this equation that they give you effectively to spit out the riser length. So now what we're going to have to do is we're going to have to basically grade in our SD3 basin. So what we know from what we've started with so far is that we're going to have to provide a minimum of 426 cubic yards. We can multiply that by 27 to get 11,500 cubic feet. So we have to provide a minimum of 11,500 cubic feet of storage in our SD3 in order to provide that minimum amount of storage. All right, so we have our number here. 11,500 cubic feet has to be provided, so we're just going to go ahead and start to draw in our temporary sediment trap. One thing to keep in mind when you're starting to draw it in is that you must have a 2-to-1 length to width ratio, so it needs to be twice as long as it is wide. Why? I don't know, but that's just one of the requirements that you're going to have to provide. So it's always better to draw it as kind of like an elongated shape versus a square shape. So I'm just going to set my ortho to something like this. I'm going to draw a rectangle, kind of like, maybe I'll change my ortho to more like that. Draw a rectangle. Okay, that's pretty obviously twice as long as it is wide. So I'm actually just going to draw that roughly, and then I'm going to provide some dimensions. So I'm going to make it like, I don't know, length 40, width 20. That's probably not going to be big enough, but we'll see. We'll work with that. So now we are going to offset this guy 4 feet, just like grading in a detention pond. So I'm just going to offset this guy for 2-foot contours. And then again, the bottom of our pond is that 1046, which is this contour right here. So we're going to have a we're just going to go ahead and set the bottom of the pond at 1046. So this guy will be 1046. I'm going to go ahead and grab some of those. Let me just go to the grading plan really quick and grab one of these blocks here, which I can't do because of this XREF. So let me go to the table here, and we'll just turn everything on really quick. Okay, that's kind of strange. Okay, now that we've copied in the topo label here, I'm I'm going to shrink this guy down just a little bit. So I'm going to change the scale Z to 0.8, 0.8, 0.8. Actually, we'll just do that. There you go. That looks a lot better. We're going to place that guy there, and that's going to be the 46. So then we've got the 48, 50, 52, okay, and then at the bottom we are going to leave it as a radius of, actually what we're going to do is we're going to delete these guys, and then we're going to set our OG or offset gap type to 1, and then offset by 4 so that we get these nice pretty curved contours here. And then we're going to do CHELEV, or change elevation. We're going to draw our low point to high point fence line, hit enter. Excuse me, that's not the right way to do that. Hang on, let's run through that one more time. Change elevation, low point to high point fence line. And then our start level is going to be, I believe, what is it, 1046? Yeah, 1046, 1046. And then the contour intervals is going to be 2 feet. So now the elevation of this polyline here, as you can see, is 1052, 1050, and so forth. So we're going to be using that command a lot whenever we're doing these sediment basins. I'm going to run the command stage storage here. I'm just going to open up this box here. I'm going to hit define basin, and then define basin from entities. I'm going to hit define basin from polylines, and then define, and then I'm going to select my polylines and hit enter. This is going to open up this stage storage volume table. So you can see the conic cumulative volume of this sediment basin here is only 10,000, and we need 11,500, so we're just barely short. So I am going to basically extend this guy another like 10 feet or so as such, and then we're going to offset 4 feet, 1, 2, 3, like the same thing, change elevation, 1046, 2 feet intervals, stage storage, define basin from polylines, define, select our polylines, hit enter, which sometimes it doesn't want to work for some reason. Okay, now we just copied this guy over because the stage storage command is giving me a little bit of trouble, but we just copy it over. Again, define basins from polylines, hit enter, and as you can see here, we've got 11,900 cubic feet. So this is as large as our temporary sediment basin needs to be to provide all the storage. So we're going to leave it with these dimensions as it is. These spots, I'm just going to go ahead and update 46, 48, 50, and 52. And then now we just need to actually grade this guy in. So here we're at the 52, and then this contour here I believe is the 60. So we're just going to have to, I'm going to go ahead and I'm just going to trace a line. I'm going to change my color back to by layer. I'm going to trace a line around this guy to like about there, and I'm just going to start offsetting uphill 4 feet. Click, 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 something like that. Again, I'm also going to open up the CDs, and I'm just going to copy in the polylines that are the contours that I need so that I can actually click with them and work with them. This is kind of the annoying thing that we were having to deal with the XREF files. But so we're just going to sit here and wait a second for this to load. Okay, now that we're loaded in, we're just going to go to our grading plan, and I'm going to select basically all of these existing contours that are polylines and copy them in so I can actually work with them. Yeah, that should be fine. Copy 0, 0. Oops. Try it again. Control C. Control Shift C, I mean, to copy, and then we're going to paste those guys in from 0, 0, so now we can actually work with them. I'm going to close back out of that CD really quick because it should be all I need. Okay, so that's the 52. So this guy is going to be the 54. So if we find the 54, it should be this guy right here is the 54. So I'm going to delete that and that. Okay, so the 54 is right here, so I'm just going to select that guy. I'm going to trim off the ends, and then I'm going to extend the 54 to that guy, and then there's the 56. I'm going to trim that off, trim that guy off. This is the 58. We're going to trim that guy and trim that guy, and then this is the 60. We're going to trim that and trim that. So we're kind of outside of that initial bounds that we drew where the wall's going to go, which isn't fantastic, but it's fine for now. So we're just going to leave that as it is, and as you can see here, we have our 60, which is still, so I'm going to change this guy to 10. 60 is crossing over the 62, so we're going to have to continue to offset until we tie back in. So it looks like that's where we're going to tie back in, so that's greater than a 2-to-1 slope. So we've got our 60, and then we've got our 62, which is going to be this guy. That guy, and then the 64 is this guy that we just drew, or just offset. Okay, so I'm going to select all of this. Okay, set that like that. And then we're going to paste more of these blocks here. So now we've got the 54, 56, 58, 60, and then 62 and 64. Okay, and then down here, as you can see, we have our 1052 crossing over our 48. So we're going to have to offset this guy. We're just going to do the same thing here, where we kind of draw part of this contour and then just offset that. Like this. So this is our 52. This guy is going to be our 1050, which is going to tie in right to that guy, and then it's going to tie in there. Okay, and then the 1050 is still crossing this 1048, so we're gonna have to offset that guy again, and then that's definitely too close to be 2-to-1, so we're gonna have to offset that guy again. That guy's gonna have to get trimmed there and there. Delete that, and then this guy here is going to get trimmed right there and right there, and then we can delete that. Cool. So now we've got our temporary sediment basin graded in. It meets the minimum required sediment storage provided. So I'm going to go ahead and I'm also going to provide, working up the side of the berm here, I'm going to give elevations going up. So we're going to have a berm width here. So actually, I kind of lied. We're going to have to regrade this. So this is our top contour here that closes, and then we're going to have a berm width here. If we go back to our field manual here, we're going to go ahead and go to SD3. I believe in the field manual they have requirements on the minimum berm width. So let's see, SD3. Okay. Installation. Okay, here's the berm width. It's gonna say, let's see, minimum top width. The fill height less than 10 feet or 10 to 15 feet. It's gonna be 8 feet minimum top width or 10 feet minimum top width. I believe our fill height for the berm is less than 10 feet. So let's go back to our CAD here. We're going from 1046 up to the top of the berm, which is 1052. So that's less than 10 feet. So our berm width is gonna have to be 8 feet. Instead of, so I'm just going to Control Z back really quick. Our berm is going to have to be 8 feet, so I'm just going to offset this guy another 4 feet there. So now there's our 52. This guy's also a 52. So there's our flat berm, which there's our 52 goes to here. So we're going to have to, oops. offset another 8 feet from there. Trim that guy. There should be 1052. Join them. And then we're going to trim them from the 1052 right there. Cool. So now here's our actual berm, and then the 1052 is right here. So that guy's gonna have to tie in. So I'm just gonna click that and then click extend. Now we can offset from 4 feet back down. So there's the 50, the 48, the 46. Okay, so the 50, we're gonna trim off. Same thing with the 48. Trim that off. My CAD's gonna freeze because I drug the trim cursor around. We'll again trim that guy off for the 48. And then the 46 here, can trim that guy, delete that. Okay, and then the 46 is running to here, so I can trim that, delete that, and then as you can see that 46 is crossing. So let me just go ahead and punch in my elevations again just so I know what I'm working with. So that's 1050, that's 1048, and then this guy is 1046. Okay, and then that's crossing the 1044, so we're just gonna have to go another 4 feet. We are in this impervious buffer here, or excuse me, this 75 foot impervious buffer, but we can still grade in that buffer, which you can't grade inside of the 50 foot undisturbed buffer. So we should be okay for the time being. So I'm just gonna grab that, trim there, and then trim that guy off right there. Okay, so now we're down to the 44, 44, 46, 48, and 50, and then the 52. All right, so now we have our berm. I'm just gonna go ahead and I'm going to dimension that just to leave that guy there. The dimension is massive because we're at an 80 scale. So I'm actually just gonna get rid of that for the time being, but you might dimension the berm just to call out that it's 8 feet. So now we have our SD3 graded in for our phase 1. So it meets the 11,500 minimum cubic feet of storage. So now what we can do is we can go back to our document here, and you can see here the minimum riser crest elevation is going to be determined by the stage storage relationship, which we have now because we have a graded in pond. Same thing with the clean out elevation. We're going to start with the clean out elevation. What we're going to do for the clean out elevation is we need to, if we go back to our sheet here, the clean out elevation is going to be at whatever elevation we reach 139.9 cubic yards. So just to convert that to cubic feet, 139.9 times 27 is 3,777 cubic yards. So what I like to do is I'm just going to go ahead and run stage storage again on our basin really quick. Okay, so it's 3,700. So just by running stage storage here, I know that at 1048 we're only at 2,500 cubic feet of storage. And at 1050, we're at 6,500. So somewhere in between 1048 and 1050, we're going to hit that 3,777 cubic feet of storage. So we just need to find at what elevation do we hit that level of storage, and that's the elevation that's going to be our clean out elevation. So I know that it's between the 48 and the 50, so it's somewhere in between these two lines. So what I like to do is I'm going to offset by 0.2, and I'm just going to offset a bunch of lines like this, as such, all the way up to the 1050, and then I'm gonna run that change elevation again. It's gonna be from 1048, okay, and then the contour intervals is gonna be 0.1. So now just to verify, I'm gonna select this guy, and you'll see that that's still 1050, but if I select one in the middle, it's 1048.7, 1048.8. So now we have a contour for every 1/10 of a foot between 1048 and 1050. So now when I run stage storage and I do define basin from polylines, and then I select my basin here and hit enter, now I'm going to have all this extra data, and then I can find which one is the closest to that 3777 and still above that number, or and so that's going to get us, well, it's ideally you want the contractor to clean out your temporary sediment trapper basin more often. So instead of looking for what number is just above, you would look for one that's just below. But this guy, 3795, is closer to 3777 than 3612 is. So this is going to be our clean out elevation, which is at 1048.7. So at 1048.7, I'm just going to find that guy, which is right here. So this is my 1048.7, as you can see from my properties pane here. I'm going to go ahead and I'm going to leave this guy on the same layer, but I'm going to change the color to yellow, and I'm going to change the line type to -2. I'm going to run PG yes on it so that it's continuous, and this is now my clean out elevation, and then all these extra lines here that I just used to run that stage storage, I'm just going to go ahead and delete those, and now I have my clean out elevation drawn out on my plans. That's also going to have to get called out with a multi-liter, so we should have a multi-liter here for the clean out elevation to get called out. Let me move this guy back over here. Maybe go to phase 2, see if it's there. Should be somewhere around here. Maybe not. Maybe it's not over here in the blocks. Either way, we can just add, I'm just going to copy one of these multi-liters here, and I'm going to call out the clean out elevation. I'm going to drag this guy down here, add a background mask, and then I'm going to call this guy out. I personally like to get somewhat tedious with my erosion control plans, but I'm going to call this out as clean out elevation. And then I like to provide the elevation in yellow, so in plan view I can see the difference. So that was 1048.7 feet as such. And then I also like to make it underlined line type like that. So there's our clean out elevation at 1048.7 feet. So that's now called out. So now we have our clean out elevation. So I'm going to go back to our temporary sediment basin design sheet. Our clean out elevation is at 1048.7 feet as such. Okay, and then it should be clearly marked on a riser, so we'll probably add a multi-liter later on for that. Now we need to calculate our minimum riser crest elevation. So in order to find our minimum riser crest elevation, we are going to refer to that Excel spreadsheet that we have. So if you navigate back to the Erosion, Georgia G. Swick, ST3 calcs, and then select this sediment basin XLS sheet, this guy's going to open up for you, which essentially, if you go through the worksheets here, this is exactly the same as the worksheet that we're currently working on. So if I just drag this off to the side so you can view it, you can see that it's, you know, volume, stormwater runoff, etc. It goes through the whole thing. So you might just start here with this Excel spreadsheet, you know, and then translate all those numbers onto this if G Swick asks you to provide this specific sheet. But we're going to start with our stage storage. So I'm gonna come back here to our CAD here, define basin, define from polylines, and I'm just going to translate this stage storage calculation that I have here. It's right here, but I'm going to drag it off to the side, and I'm going to input it here in the Excel. So the bottom elevation is 1046, and then 1048, 1048, or excuse me, 1050, 1052, and then I'm just going to get rid of those for the time being, and then I'm going to, might give us a funky number, but we'll see. The area for the 1046 is 1,000 square feet. Okay, and then 1610.27, 1847. Oh, that's not right. 2321.06, and then 3132.39. Okay, so our total volume, our conic cumulative volume is 11,929, which is fine. The volumetric clean out that it's going to spit out was 1046.6, which doesn't seem exactly correct to me, but I think it might be because of these guys here. Let's go back. Oops. Okay, so we have this data here that's inputted. That's probably not correct. We're going to go ahead and navigate to the peak discharge file here. The total basin area was 6.3 something? 6.36 or 6.3. Let me go back to my calculator just to verify really quick. 6.36. Okay, the TC is 5 minutes, and the curve number I'm not exactly sure of yet, to be honest. But once you fill out your information for your peak discharge calculations, it should update for your stage storage. Okay, so for our precipitation depth, you're going to go to the NOAA Atlas 14. You're going to punch in the address of our site. So I just punched in the address of the neighboring property. And then you're going to make sure you're on precipitation depth, and then you're going to select the 25-year 24-hour storm here, which is 6.21 inches is going to be the depth there, which is what I just inputted right there. And then the 2-year peak discharge, same thing, 2-year 24-hour, which is going to be that guy, which is 3.91. As such, we'll go back to our stage storage, and then we should have updated values here. Okay, and you're also going to want to make sure you update your total area draining to your basin as 6.36 and your disturbed area draining to the basin, which we don't know yet. We're just going to leave that blank for now. Now we're going to go back to our stage storage, and now our numbers look correct and much more like the numbers we got from our multiliter. So our total volume here is just over 11,500. Storage volume required is 11,500, and the volume at clean out is that 3777 that I was talking about. It just rounded up to 3778. And the elevation that it said is the clean out elevation is 1048.6. We calculated 1048.7, but I'm just going to leave it 1048.7 for now. We know that we're obviously in the ballpark by following the Excel sheet and based off of our hand calculations. So update this value here in the worksheet, and then update these peak discharge calculations based off of the depth tables here from the NOAA Atlas 14 at your geographical location. Now that is going to spit out our minimum riser crest elevation, which is going to be 1058.1. So I'm going to go ahead and fill that out in the sheet here, 1058.1, or excuse me, 1051.8 feet. And the riser length is going to be the minimum elevation of the riser crest minus the lowest elevation of the pipe at riser. So that's basically the length of the riser, or how tall the riser is. So I'm not exactly sure what the lowest elevation of the pipe at the riser is quite yet, because we haven't designed our outlet pipe, so we're going to come back to that later. Now moving on to stormwater runoff, it's going to ask us to compute the peak discharge from our 2-year and 24-year or 25-year 24-hour storm events. We already did that by doing this peak discharge tab here, so that's going to punch out these two values for us right here, which we're just going to go ahead and punch in on this sheet right here, 14.5 CFS and 30.9 CFS. Okay, the surface area / configuration design, we're just going to run through all these calculations, which are basically punched in already in our Excel sheet here, except for the average width and the required length. So the average width, we've designed a pond that is the same width for the entire length of it, but if you have a weird shaped pond that's something like, I don't know, it's shaped more like a trapezoid or something, then you would just take the average width, which would be, you know, the width like about halfway, or well, actually it'd be like 2/3, I think, actually, but you take the average width. So our width for the entire length of our pond is 20 feet, and our length is, I believe, 60 feet, nope, 50 feet. So back to our sheet here and our Excel sheet, our average width is 20 feet, and then the required length would be 40 feet. Our available length is 50 feet. So we satisfy the 2-to-1 ratio. So again, we're just going to translate this guy over here, and then we're going to fill in all these values that it spit out for us. So it's going to be that 14.5 CFS, which is going to equal to 0.15, and the square footage times the acreage, 0.15 acres is going to be 6,334 square feet. The available area, let's see, we're just going to say out, it says out of range. We're going to leave this blank for now because we haven't done our riser length yet. The available area, yes or no, we're going to be yes, so I'm just going to put Y for yes. The average width is 20 feet, and the required width is 40 feet. So that's going to be 20. The required length is 2 times 20, which equals 40. Move that up just a little bit, which equals 40. The available length is 50. So yes, we meet that requirement as well. Moving on to our principal spillway. So our principal spillway is going to be the outlet pipe coming out of our SD3. So the capacity for the principal spillway is going to be equal to our 2-year storm Q, which is at 14.5 CFS. The vertical distance between the center line of the outlet pipe and the emergency spillway crest is a height that we're going to specify, which we haven't really gotten to yet. Moving on to the total length of the pipe, this is going to basically calculate the length of your pipe, which you can kind of just get from designing in your CAD. So we're going to go back to our CAD here, and now we're going to think about where we want to locate our outlet pipe. So we're going to want to locate our outlet pipe running through the berm, and it's going to want to exit at the lowest point. So probably the best location for us to have our outlet pipe is going to be running somewhere like this. So I'm just going to move these elevation guys out of the way here. We're just going to resituate these. That guy can get deleted. We're also going to set up our diversion ditch. Adjust our diversion ditch that's actually diverting into our pond here. So we're probably just going to kind of have this guy, change course just a little bit and then move like that as such. Move this guy back to here, and then we're going to offset that again just to draw out our diversion ditch. You don't have to do this, you can just leave it as the directional line. I like to do it though, just because it makes them look a little nicer, I think. I'm going to delete this outer bounds for our SD3 here. I'm also going to go ahead and add the block for the SD3, so I need to grab this guy, temporary sediment basin. We can provide a sheet that have all our calculations from our sheet, or we can also provide this multi-liter here. So I'm going to provide the multi-liter that shows our calculations as well. It's typically what we like to do. So we're just going to put that SD3 logo right there in the middle, and then this multi-liter is going to point to the symbol, and we're basically just going to translate our calculations that we've already done. I'm going to go ahead and add a background mask to that. So again, minimum storage, an area, 6.36 acres. The minimum storage is going to be 6.36 times 67. I can just go ahead and clear my calculator off. 6.36 times 67. And then that is going to be 426.1 cubic yards. The sediment storage we provided 11,900 cubic feet. I'm going to divide that by 27, which is 440.7. So you're just going to put the amount of storage that you provided inside of your basin. The clean out storage is going to be that acreage, 6.36 times 22. So we're going to do that again, 6.36 times 22, which is going to be 139.9 cubic yards. And then the clean out elevation to be marked on a stake or riser. And then again, I like to put my clean out elevations as yellow and underlined, and then that elevation is 1048.7 feet. Get rid of that feet as such. Okay, now we have our multi-liter here calling out our SD3 sediment trap, and then our pipe here, our outlet pipe. Another thing that you can do is you can use the outlet pipe for the detention pond, and that kind of doubles as your outlet pipe for this, but because we have this weird pond that doesn't seem to have a designed in outlet control structure yet, we're just gonna not worry about that for now. And our principal spillway is just gonna be a fine line width. We'll just say it's gonna be an 18-inch, might be a 12-inch pipe. Usually these are narrower pipes, so we'll just say this is a 12-inch pipe for now. Throw it on our BMP layer, and then we're going to make it the dashed line type, and I'm going to change the line type scale to like 0.5 so it looks more like a pipe, and then I'll run PLCC on it. So now we have a pipe here, and then we're going to have our riser located right here. So this is going to be our riser. This is typically how we show our pipe and riser, and then we also have, I believe we have blocks here to call out the riser as well as the principal spillway. Okay, so to calculate this capital H value, what we need to find is we need to find the minimum emergency spillway crest elevation. So our riser crest elevation is going to be basically our bottom of the pond plus our minimum riser length. So if I pull over our sediment basin Excel sheet again, our minimum riser length is going to be 4.2 feet, right? Because the lowest elevation of the pipe at the riser, I've decided from our CAD, is that the invert of this pipe is going to be 1046. So 1046 is the bottom of our pond, so that's effectively 0 feet. So if I go back to our Excel sheet, 0, 4.2 feet. So now we've got 4.2. Okay, so our minimum riser crest elevation is 1051.8. So just to walk through this one more time. Okay, so based off of our minimum riser crest elevation, which is 1051.8, so 1051.8 minus the bottom of our pond, which is 1046, which is 5.8. So the minimum riser crest height is the verbiage that they should use, is 5.8 feet. So the riser length is going to be 5.8 feet. Okay, so now we can move down to our emergency spillway crest elevation, which is going to be 6.8 feet. So the emergency spillway crest elevation is going to have to be 1046 plus 6.8 feet, which is going to put it at 1052.8 is going to have to be the crest elevation. So that's going to run us into a problem because our berm here, as you can see, is only up to 1052, but the minimum emergency spillway crest elevation is 1052.8. So we're either going to have to do one of two things. We're going to have to lower the depth of our pond, or we're going to have to raise up the height of the berm. All right, so we're going to first try to just lower the depth of the pond here, or excuse me, of the infiltration trench. So not infiltration trench, temporary sediment basin. So I'm just going to offset again 4 feet, and we're going to provide a little bit more volume here with this 1044. It's going to be right here. So I'm just going to go ahead and copy this guy, label this with the block as 44. Okay, and then if we go ahead and run stage storage on this guy again, so some of the things that are going to change from us making it a little bit deeper is going to be the clean out elevation, as well as the top of the, the emergency spillway. So now our cumulative volume that we get is 13,408. So I'm going to go ahead and I'm going to plug in all of this back into the Excel sheet here into the stage storage. So I'm going to drag that guy over to the side, move that, and bring this back so you can see what I'm inputting here. So I'm going to do 1044, 1046, 1048, 1050, and then I'm going to insert, and that guy's going to be 1052. We're going to update this Excel sheet so that it, oh, okay, well, not sure why it's doing that, but anyways, we're going to punch in all of these updates. So this guy should now be, let's see, 504, 1000, 1610, and the 1050 should be 2321, and then 1052 is 3132. As such, no, it's going to be 3132. So we're just going to copy all this. I'm going to have to do this kind of the slow way. Except this is going to be 10 and 9 equals. Okay. And then this guy, everything's going to go up 10, 7. Okay. That still doesn't really make sense. Oops. As such, there we go. Okay, the depth is just going to be 2, and then this guy here, we're going to copy all that, and we're just going to have to update this sheet like this. There's probably a faster way to do this. I'm just not that smart. So we're just going to do it this manual way, like that. Not all that good with Excel. 10, 10 equals enter. Okay. Okay, total volume 18, that is not correct. Oh, excuse me, so it should be, there we go, 504. 8 and 7, 9 and 8. Okay. 8 and 7, 9 and 8 should be 6, 5, 7, and 6. 504, 1000, 16, 10, 23, 21, and 31, 32. So now we're at 13,404, which matches our 13,408 that's right here. So we're going to go back to the Excel sheet. Okay, now that this guy is updated, this guy is going to be equal to G10 over 27. Okay, so now we have, this guy says out of range. Going to pull that guy there. Cool. Same thing with that guy. Okay. Okay, now we can go back to our minimum riser crest elevation, which is now 1051.3 as opposed to 1051.8. So that dropped us down a half a foot, which means that our minimum riser crest elevation should be 1051.8 minus, now the bottom is 1044, which is going to be, or excuse me, 1051.3 minus 1044 is going to be 7.3. Okay. And then now our minimum guy here needs to be 8.3 feet, so it's going to be 1044 plus 8.3, which is going to put us at 1052.3. So that's still above our berm height of 1052. So we can either try to make it deeper again, or we can just try and make the pond taller, which is what we're probably going to have to do. So I'm going to, off camera, for this time's sake, regrade this guy such that our top of the berm here is 54, and then we'll come back.